Ready? Okay. So welcome to the 5th lecture in this course on nonlinear dynamics and chaos. I'm going to spend about 3 minutes, maybe, finishing up a last little chunk of work from last time, which is about periodic orbits in maps. And then we'll spend the other, 72 minutes talking about fractals, because that's the topic of problem set 3, which is due next Tuesday, rather. So just by way of review, I talked to you last time about an ordering of the natural numbers proved by, or involved in a theorem proved by a Russian mathematician named Sarkovsky in the early 60s. Oops. Apologies. And Sarkovsky constructed the following ordering on the natural numbers. This is from your notes last time, so don't worry about copying it down. 3, 5, 7, all the odds, and then 2 times 3, and so on and so forth. And then it comes down the end like that. And what Sarkovsky proved was that if you have a map of the real line onto itself and a couple of other minor conditions, and you see a period k orbit, so let's say we see a period 7 orbit in that map, then what Sarkovsky proved was that we would also see all these other periods at some other point in the parameter space of that map. So if you see a 5 cycle, you'll see a 7 cycle, a 9 cycle, 11 cycle, all that kind of stuff. So he proved that theorem. And then in 1975-ish, James York came along with a paper called Period 3 Implies Chaos, which was essentially a corollary of Sarkovsky's theorem, which York didn't know about, so it doesn't mean that it was less of a piece of work for York to do, but Sarkovsky had actually proved a more general result first. So, so if there exists this thing is wiggly today. If there exists a period k orbit in a 1D map of the real line onto itself, then there is a period L orbit for all L to the right of k in Sarkovsky's ordering, and 3 happens to be the first number in that ordering, which is equivalent to York's paper that said period 3 implies chaos, because chaos in a map, and we won't talk about this because we are not going to do very much more with maps at all, but there are various definitions of chaos in maps, and one of those definitions is all periods are present. That's the third piece of a 3-piece definition for maps. So all periods being present is equivalent to chaos in maps. There is another ordering of the natural numbers that plays a role in the bifurcation diagram. This just says if you see a period k orbit, you'll see a period L orbit for all L to the right of k in the ordering. It doesn't say that they will turn up in that order or at what R value. It just says they will turn up. It doesn't say in what order or where, anything like that. The U sequence is a slightly more actually a lot more powerful sequence. And it starts out like this, 1, 2, and then 2 times 2, and then 6, 5, 3, 2 times 3. And the U sequence has a depth, so you can do the U sequence kind of up to a certain depth, up to depth 6 here. What I mean by that is you can take a deeper and deeper slice, in which case if I went up to depth 12, there'd be more stuff in here. But I'm only taking a slice off the top of this thing. And what's more powerful about this is that not only does this tell you if you see a period 1 orbit, you will also see a period 2 and a 4 and a 6. It tells you that this is the exact order in which they turn up. Okay, so it's the order of appearance of stable periodic solutions as R changes. It doesn't say at what R values yet. It does tell you that first there's a 1, then there's a 2. By the way, you've actually drawn yourself a picture of that. What's that piece of the U sequence? 1, 2, 4.
The period doubling.
That's the period doubling bifurcation sequence at the beginning. What's this thing? That piece of it.
windows.
That's that big window of order that has a 3 cycle in it, then a 6, then a 12. That's that. So you can see the structure of the periodic orbits a little more in depth in the U sequence. Now, the paper in which the U sequence is described is on the problem set 2 bibliography. And I don't know if you've noticed, but on each of the problem sets there is a bibliography. What I do with that, the reason that I put those on there and the idea of me doing that is that if you, this is kind of like the seminal paper, the next seminal paper on each of the topics I've talked about that week. Okay, so the bibliography is not assigned reading in this course. The bibliography is if there's something in this course, like I've said something about Feigenbaum, I've said something about the U sequence, I've said something about James York's paper, I put those papers on the bibliography so that you can go find them if you want. And most of them, as you can see by my, my notes here, you can find in the library using these notes, so it's on reserve. This one is in a reprint collection, which I have on reserve. This is in a different reprint collection. So this is a map of if there's something that you're interested in this course or something that confuses you, this is the next place to go for each of the things that I've talked about that week. So that's what the purpose the bibliography serves here. And here is the paper on the U sequence. I don't think I have Sarkovsky's paper on here, but I can give that to people who are interested. It's pretty heavy going. Well, so's this. Okay, so that wraps up our treatment of maps, and we're going to now move to fractals. And the reason that we talk about fractals in a course about nonlinear dynamics and chaos is this statement right here. This is why. Many chaotic systems have some fractal state space structure. Notice that this does not say all. Okay, and that is a pop science misconception about chaos, that fractals equals chaos and chaos equals fractals. That is not the case. There are a lot of fractals that have nothing to do with chaos, and there are some chaotic systems that do not have fractal state space structure. So chaos and fractals, it's not this, and it is most certainly not that. Okay? However, there is a connection. Depending on how careful people are, they use different ones of these words. I use most because it does seem that it is the case that it is most chaotic systems have some fractal state space structure, but it is important to remember that this is not all. And that is a popular misconception here. I've waved my hands a little bit about fractals for the past couple of weeks, a couple times, and I've used the term self-similar. Self-similar. I've said if you zoom in on the bifurcation diagram of the logistic map, you'll see small copies of itself. If you keep zooming in, you'll see more and more times you'll see the same stuff. You keep zooming in with the microscope, you'll see self-similar structure. There is a formal way to think about fractals, and we'll get to that later today and perhaps on Thursday. So just some examples. I drew the Cantor set for you on the whiteboard last week, and I'm going to draw it again now. The way you draw it actually works best if you have an eraser. You start out with a line segment, and I'm going to do the middle third. Cantor set, just by example. You start out with a line segment, and you erase the middle third. And then you do that over again. And then you do that over again. So at each iteration, so here's a bunch of iterations. I'm taking out the middle third of each chunk of line. Okay? And if you do that an infinite number of times, and you zoom in on here, and you zoomed in on here, and you zoomed in on here, and you zoomed in on here, in the limit of large iterations, you couldn't tell the difference. That makes sense? Right, the way I've got it drawn there, obviously you can kind of tell the difference. But in the limit of large iteration, all of these will be indistinguishable. Distinguishable. In the limit of large iteration. this iteration business. Okay? So each of the things in my yellow circles is a Cantor set. So the Cantor set contains small copies of itself. It contains an infinite number of small copies of itself. You can drill down, you can repeat this drilling down process, and you will always see a middle third removed Cantor set. We could also think about other sizes of Cantor sets. We could think about removing the middle, I don't know, 5th, 6th, 9th, 7th, whatever. Okay? And one of the things about fractal dimension is you can imagine that the middle third removed Cantor set versus the middle, I don't know, say 7th removed Cantor set, one of them has more stuff in it than the other. But the standard definitions of dimension don't let you express that. And that's what fractal dimension will let us do, is to say that the top thing, because at each time you're taking out a bigger chunk of it, the top thing has fewer points in it in some sense than the bottom thing. We'll get back to that. So this is the Cantor set. It is a fractal that lives on the unit interval. Another example is the Koch curve, or Koch curve if you're German. And the way you draw the Koch curve is you start out with an equilateral triangle. It's not very good, but you get the idea. So an equilateral triangle. And the iteration sequence here is you take another equilateral triangle of 1/3 of the size of each edge length and stick it to each of the open edges like that. Okay, so the iteration is this edge here. You take, it's an exposed edge, you take another triangle that's one whose edges are 1/3 the length of that side, and you stick it to that edge. So the next sequence, the next iteration would be, and you can draw them different ways. Sometimes people, will stick another triangle here or not. They're all different Koch curves. Okay? What am I going to see in the limit of large iteration if I zoom in here or here or here? I'm going to see the same thing. Okay, I'm always going to see the same thing. So I'm always going to see a Koch curve here, also sometimes known as the Koch snowflake. Because depending on how you do this, you get something that looks a lot like a snowflake. So there's this notion of iteration and self-similarity. Two notions that are critical to fractals. And you've also seen another fractal. The bifurcation plot of the logistic map looks something like this. And if you zoom in here, or here, or here, or here, all of those places, you'll see another bifurcation diagram of the logistic map that has period doubling bifurcation sequences and yada, yada, yada. Okay, so this thing is self-similar. Okay. So that thing is self-similar. There are also there are lots of wonderful fractals. This notion of iteration, the devil's staircase is something where each stair has stairs within it, and each of those stairs has stairs within it. So that's why it's called the devil's staircase, is because if you have very short feet, it takes you an infinite amount of time to get up it. So it's hard to draw. I don't know how to draw it, but think about each stair all of a sudden gets another stair in it, which gets another stair in it. So there are lots of wonderful fractals that people have come up with. The Mandelbrot set is another wonderful fractal. Okay. People have seen or heard of this? Okay, a bunch of people have. The Mandelbrot set is the set of complex numbers. Okay, complex numbers C in the complex plane. I think we've talked about this. The complex plane. If you have a number C that has a real and imaginary part, so C is A plus IB. This is the real part of the number C on the horizontal axis. Yes, we talked about this in the context of the Newton's method on x to the fourth minus 1 equals 0. So graphical representation for numbers in the complex plane, you plot their real part on the horizontal axis, their imaginary part on the vertical axis. And the Mandelbrot set is the set of complex numbers. I started this up here. I'm going to finish it down here. The set of complex numbers for which the following iteration sequence does not blow up. Okay? For which the sequence C squared plus C squared plus C squared plus C, etc. See what I'm doing? I'm squaring the last number and I'm adding C to it. Does not blow up. That's the Mandelbrot set. So it's the points C in the plane. So here's A, here's B. This is the representation of the number A minus IB. And the Mandelbrot set is the set of complex numbers C in that plane such that if you perform this operation, if you square the number and you add it to itself, and you square that result and add it to C, and you square that result and add it to C, that iteration sequence does not go bang. Now typically, the Mandelbrot set is certainly interesting, but what people do, and it kind of looks like this, and it has tails and things like that. What people typically do is they plot the Mandelbrot set in black, and they use a color code on the other points. So they use a color code to say, you know, this point blows up at such and such a rate, and this point blows up at such and such a rate. So the way people plot these is they generally plot the Mandelbrot set in black, but then there's all this other interesting stuff around it that is color coded to represent or to capture how fast the points that are not in the set go boom. Okay, so that's what the Mandelbrot set is. So let me see if I can get to PowerPoint. There we go. By the way, I've got the website up here. I wanted to show you a couple things. This is the website for the class, which I sent you. You have the link for in the syllabus. There's all sorts of handouts on the top. A little bit further down are some written notes. Many of you have rummaged around here, I'm sure. Some of these are useful. It's when I get unhappy with a chunk of the textbook, I rewrite it, and that's what those 6 bullets are. A little bit further down is a link to the CATE website where you can find the recorded lectures, and also copies of the annotated slides for each lecture. So when I finish up, it asks me if I want to save the annotations. I say yes. I put them in PDFs, and that's where those are. And then there's all sorts of junk down here, much of which is pretty interesting. This website right here is the Google Labs Julia Map website, and there is a problem on problem set 3 asking you to go there and dig around in a couple fractals and pick out an interesting part of one of the fractals and print it out and hand it in. Many browsers, this website doesn't work. If that's the case for you, find some other interesting fractal on the web and print a little bit of it out and send it in. So if this particular website doesn't work for you, feel free to dig around and look at someplace else. But what I wanted to show you today was the Mandelbrot set. First of all, let me back up. There's the whole thing right there. That's my bad drawing of it, you saw. Okay, so that's the whole thing. And what this video is going to do is zoom in, and you'll see some amazing, beautiful structures as you zoom in. Ah, what did I do? Sorry. It got me, didn't it? There we go.
Oh, it's like behind.
Now it's hanging up. Let's kill this off, and let's try this again. Full screen. And you can probably start to see, like this little guy right here. Oops, I can't do it. Go away. That little thing that's turning up in the middle of the screen looks like a Mandelbrot set. It is. It's a piece of the Mandelbrot set. Looks like the Mandelbrot set itself. So you can see why people get really immersed in drawing these pictures. And people can spend hours and hours and hours playing with color maps to bring out different kinds of structure. And what's amazing to me is that all of this structure comes from a simple iteration sequence. Square the number and add that number to itself. And do that over and over again, and you get this amazing amount of structure. And all of those black thingies are points that do not blow up, and they're all connected. And you can go an infinite amount into this. Okay. Go away. All right, so that's the Mandelbrot set. And yeah, I missed some lumps here. There was a lump out here and a smaller lump. But anyway, so you zoom in and you zoom in and you zoom in, and you go this angstrom-wide chunk right there, and you find another whole Mandelbrot set. So this is an infinitely complex object, which is pretty amazing because of how simple the mathematics is to generate it. So there is a nice canonical fractal. And there's the YouTube link if you want to look for it right now. It's also posted on the course webpage, as you saw. There are lots and lots of examples in nature, lots of phenomena, lots of objects that exhibit fractal structure. But you have to be a little bit careful. I didn't say they are fractals. I say they exhibit fractal structure. Because technically speaking, the strict interpretation of the word fractal means you have to do that iteration an infinite number of times. Okay, so to strictly be a fractal, you need to be able to zoom in on it an infinite number of times and still see more stuff coming at you. So a tree, for example, has a trunk, and then that trunk has a branch, and another branch, and a branch, and a branch, and so on and so forth. So there is branch on top of branch on top of branch, but the notion of doing that an infinite number of times doesn't make sense. Okay? But there is some fractal structure in the structure of a tree. Mountains tend to have, bumps, and then they'll have another bump and a little bump and so on and so forth. So mountains are often fractal. Coastlines are fractal. So a coastline will have a bay, but then it will have a bay within the bay and another bay within the bay. And this set off a wonderful thought experiment years and years ago entitled, "What is the length of the coastline of Britain?" Anyone familiar with this? I see one or two nods. So the question is, how long is the coastline of Britain? The answer is, depends how long your feet are. Right? Because if you are a snail or a person or a bacterium, you're going to follow different numbers of those little tiny bays. Right? So if you're really, really short feet, you're going to get a different answer than if you have bigger feet. So, and that's because coastlines are fractal. There are a lot of people in our civil engineering department who think about drainage basins and creek systems. So a creek going up, Boulder Canyon has all these branches and branches and branches. It looks kind of like a tree. And each of these things drains a certain basin. Drains a certain basin of the canyon. And those drainage basins are fractal as well. Again, have some fractal state-space structure. Clouds are fractal. They have bumps, and then those bumps have bumps. So people compute fractal dimensions of clouds. Essentially, anything that somebody feels the need to put an object in the picture for scale, like a geologist when they're taking a picture of a rock, they often put their hammer there so that you can tell how big it is. That lack of the ability of the eye to perceive scale often corresponds to objects that are fractal. So it's hard to perceive scale when things are fractal, and that makes sense because if you look at them from here, they look the same as if you look at them from here, and so that makes scale very difficult to deduce. All right, let's go back to the Koch curve for just a sec, wherever it is. There it is. Think about the iteration sequence that goes from this to that. At each step, some piece of the perimeter of that object is undergoing that kind of transformation. What does that tell you about the length of the perimeter?
Increasing?
It's increasing. So in the limit of large iteration, how long is it?
Infinite.
It's infinitely long. So the perimeter is infinitely long. What about the volume enclosed? you think? So at each step, you're taking something that's this big, and you're adding those chunks to it.
That's just finite because it can all fit inside of a circle.
Right, so it's finite. So the volume, volume is finite. The enclosed volume is finite. So, another example of fractals in nature is lungs. This is actually a pretty good design because you have something that has a very large volume, or sorry, a very large perimeter, excuse me, inside a bounded volume. So there's the rib cage, which bounds the volume of the lungs, but you want the lung surface area to be very large because that's how the blood and the oxygen get in contact. So having fractal lungs is a very good design. I'm not implying the existence of an intelligent designer. Okay, yes, sir.
I recall something from biology that our lungs have a surface area of several meters square or something like that.
Yeah, so for those of you remotely, it was just brought up that lungs have a surface area of multiple meters squared, and inside, you know, a ninth of a cubic meter or something like that. But again, lungs aren't really fractal, they just have some fractal state-space fractal structure, okay, because you can't zoom in below the alveoli and get any more structure. Anyway, so bounded volume, large surface area, fractal, lungs, so on and so forth. Some of this relationship between, or the fact that a lot of things in nature have fractal structure suggests another application of fractals, and that's in computer graphics. So people, a lot of people have used fractals to generate different kinds of structures in computer graphics. In this picture, the rocks, the clouds, and the trees are all fractals. So it's a nice way to hack together a fractal in computer graphics. And people have even written poetry about this kind of stuff. Okay? So fractals are cool. They have inspired poetry. They are useful in terms of generating pictures of nature. They're useful in terms of describing nature. And the reason that we talk about them is, again, in this class, because there is a relationship between fractals and chaos in the sense that there is fractal structure in the state space of chaotic systems. And I'll make that more precise. I'm being careful because it's true of attractors, it's true of basins, it's true of boundaries. So there's three different pieces where this turns up. And in order to think about this more deeply, we need to think about the calculation of fractal dimension. Now, you probably know this topological dimension quite well. It's the minimum number of coordinates that you need to describe where you are in an object of a certain topology. So, for example, in a point, if you are sitting on a point, you need 0 coordinates to say where you are on that object. Okay? But if you're on a line segment, you need 1 number to say where you are on that line segment. If you're in the plane, you need 2. If you're in 3D space, you need 3. So that's a hand-waving definition of topological dimension, is to describe where you are here, or where you are here, where you are there. How many numbers do you need? And that's the topological dimension. You can't use this construction to say anything about the relationship between a middle third removed Cantor set and a middle, 27th removed Cantor set, because both of those are really one-dimensional. Well, not quite. Okay. So where would a Cantor set fall on this continuum? Where would a Cantor set fall on this continuum? It's kind of more than a bunch of points, but it's not quite filling up the line-ish. Okay? And the word more than a bunch of points, when you're doing topology, you can't, standard topology, you can't do that. So where's the Cantor set fall between here? So it's fractal dimension allows definitions between 0 and 1, between 1 and 2, between 2 and 3. Where do you think the Cantor set falls here? Okay, so the Cantor set is in here someplace. Where's the Koch curve? Somewhere in here. Okay? So there's this notion of kind of betweenness between dimensions, which does not exist in traditional topology at all. Okay, so a Cantor set is, air quotes, more than a bunch of points, but it's less than a line segment. Okay. So fractal dimension is just a different definition of dimension that allows this, that captures that. The originator of this notion was Mandelbrot, the same guy who that set that we looked at is named after. It's just a different definition that allows non-integer values. Okay, so it allows non-integer values. It's just a different definition, capturing that formally. Now here's a concept we're going to need to talk about this, the notion of a ball of radius epsilon. And when we think about this physically, think about a baseball, just a baseball, physical baseball. That's a ball. That is all of the points that are within some radius of the central point are in that ball. Okay. You could think about the surface of the ball, and that's a spherical shell. That would be all the points that are exactly epsilon from the central point. So the spherical shell of the ball is all the points that are exactly epsilon from the central point. All the points that are within epsilon, that is, the distance between that point and the center point is less than or equal to epsilon, that's the solid ball of radius epsilon. So we use the Euclidean norm when we think about distance, so our balls look like that. Okay, and this is a 3D ball. But there are other ways to measure distance, right? And you've heard the term norm, I hope, in some of your math classes. Different norms are different ways to measure distance. So the Euclidean norm, if I'm at, here and I want to get there, I take, and this is, x here and this is y. The distance here is the square root of the sum of the square root of x squared plus y squared. That's Euclidean distance. But if I'm in Manhattan, that doesn't work, right? These are avenues, these are streets, and you can't walk through buildings. So Manhattan distance, okay, would be, you got to go walk over from, from Broadway to 6th Avenue and up 42nd to the 48th. That's a different kind of distance. Then what would the distance be between, if this is 2 blocks and this is 2 blocks, what is the Manhattan distance between those 2 points? Or, well, if those of you from Manhattan know that these are longer than those, but that's okay. So it's 4, all right? I was born kind of here. 60th and 1st. There we go. Okay, so you can imagine that there are different ways to measure distance, and these are 2 other ways to measure distance. And we're not going to go into the technical details of how to calculate them very much because we're not going to need that. We're just going to use them. But I am going to show you a picture that says what the ball of radius epsilon looks like if we're using a different norm. That's what the ball of radius epsilon looks like if we measure distancing with the Euclidean norm. With the L1 norm, looks like that. Anyone know what it looks like in the L infinity norm? Square. Okay, and you can actually draw these things. You draw them on top of each other. It's a bad drawing, but you get the idea. So that's how they all look. So you can think about them as, I don't know, the way we measure stuff, and then there's kind of the pessimist norm and the optimist norm, or whatever you want. Okay, so the ball of radius epsilon is all the stuff inside here. And the way that we're going to calculate fractal dimension is we're going to figure out how many of those balls it takes to cover the object. So we have some funky looking object. And what we're going to do is take balls of radius epsilon and figure out how many of those yellow things we need to cover the purple thing. And then we're going to change the ball size. You get the idea. I'm not going to completely cover it. In general, maybe I will, if the ball size gets smaller, what can you say about how many of them I'm going to need to cover the object? Generally, more, okay? And the amount of more that is the way that the number of balls scales with the size of the balls, that is the definition of dimension. Okay. So here's one definition that we'll use. It's called the capacity dimension. Strogatz calls this the boxed counting dimension. There are lots of synonyms and conflicts about names in this field, so you've got to be a little bit careful. So the way the capacity dimension is defined, the capacity dimension, D sub C, is defined as the log of the number of balls of radius epsilon over the log of 1 over their size in the limit as the ball size goes to 0. Okay, so this is the number of epsilon balls to cover the object, the set, and this is the size of the balls. This is one definition of fractal dimension. It's arguably the most common. It's the one that you will calculate pencil and paper in problem set 3, and you'll calculate again with a computer in problem set 10. Okay, you'll start with this one.
Going back to your drawing of that, it seemed like the yellow ones were heavily overlapping and the red ones were mostly not overlapping. Are they supposed to be one or the other? Or?
I was just drawing uncarefully. So the question is, someone noticed that the yellow balls overlapped a lot and the red balls didn't. That's mostly, there's going to be more overlap with the bigger balls. That's certainly the case. Just because, you know, they're, you can prove that from geometry, that they're going to they overlap more, but that doesn't actually matter in this calculation.
Well, but I guess if you're allowed to overlap them, can't you just put an infinite number in there?
Minimum number of balls.
Okay.
Yeah.
Yeah, I was going to ask, because if we're dealing with a fractal here, isn't the number of balls going to get infinite as the fractal gets infinite? Because you can just cover along the line of that fractal and have those balls just go around.
So the question is about this is eventually going to go to infinity, and that's true, but there's going to be a 1 over small down the bottom, and we're going to see who wins. Yeah, good question. Intuition. And we're going to need Lhopitals Rule to deal with this. Okay, and I'll come back to that if you don't remember that. Okay, so let's do some examples, just to give you a feel for this. If I have the unit line segment, I want to calculate the fractal dimension of this, and I better get the answer 1, because fractal dimension allows for non-integer values, but it should collapse to integer values when you apply it to something that has dimension, standard topological dimension of 0, 1, 2, or whatever. Okay. All right. What is the shape of a ball? What's the shape of this object? What kind of shape of ball am I going to use? This is a one-dimensional object. Okay. So I'm going to use a one-dimensional ball. What does a one-dimensional ball look like? Little chunk of line. Okay. Now there's a technicality here. We can use a ball either of radius epsilon or of diameter epsilon. So it doesn't matter if you use a ball of radius or diameter epsilon. Both okay. And the reason for that, going back to this equation, is if you use balls of radius diameter epsilon, you're going to have half as many of them, and so you're going to get a 2 on the top and the 2 on the bottom that are going to cancel. So this epsilon ball can be either radius or diameter. Both are okay. So here I'm going to use balls of diameter epsilon here because it's easier. Now if I have a ball of ball of diameter epsilon, here's my epsilon ball. How many do I need to cover the object? 1 over epsilon, because if epsilon's 1, I need 1. If epsilon's 1/2, I need 2. If epsilon's 1/3, I need 3. So in general, it's going to be 1 over epsilon to cover. Okay. So the fractal dimension, the capacity dimension, plugging back into that equation, it was the limit as epsilon goes to 0 of the log of the number of balls of radius or diameter epsilon that I need to cover the object. That's 1 over epsilon. That's going in there. Over the log of 1 over epsilon. I don't need Lhopitals rule to figure out what that is, right? What's that? 1. And that's a good thing, okay? And that is the definition of dimension, is that the number of balls that you need to cover the object scales linearly, inverse linearly, with the size of the balls. That is one-dimensionality, if you're like that. Okay, so for some of the stuff you're going to do, calculations you're going to do, the answer to looking at these kinds of things is going to require a little bit more than just saying, well, that's obviously 1. So you might need to use Lhopitals rule. So Lhopitals rule is what you deal with, what you use when you have some stuff over some other stuff, and you're taking a limit of that ratio either as something gets big or something else gets small. And you can't solve it by inspection. What do? Anyone remember? Take a derivative, so you do the same limit of stuff 1 prime over stuff 2 prime, and you keep taking derivatives until the answer becomes obvious. That's Lhopitals rule. Should be a Lhopitals rule there. So for example, if I want the limit as x goes to 0 of, I don't know, x squared over x, that you can figure that out because you can tell who's going to win, right? But if you were being careful, they say, well, it's 2x and that's 1. Now it really becomes obvious who wins. The numerator wins. So that would be 0, okay? But it's not always so obvious if these are complicated things. And so you need to use Lhopitals rule in these situations. So for our next example, we're going to calculate the capacity dimension of the unit square. This is 0, 0. This is 1, 1. This is a two-dimensional thing. We're going to use two-dimensional balls. We could use balls like this, or we could use balls like this. That's one of the things about norms is you should be able to use any one of them, right? Not always. We'll come back to that. Which of these is going to make life easier for us? The bottom one. So here's the ball we're going to use, and it's going to be epsilon wide and epsilon thick. So it's an epsilon by epsilon ball. How many of those am I going to need to cover the thing? Well, if it's epsilon squared. So if they're 1 by 1, I'm going to need 1. If they're a half by a half, I'm going to need 4. If they're a third by a third, I'm going to need 9. Okay, so it's 1 over epsilon squared. Okay. So capacity dimension of this thing, limit as epsilon goes to 0. Oops, lost my log. Log 1 over epsilon squared. Log 1 over epsilon. And you can do that by inspection, or you can do it with Lhopitals rule if you want. Remember the rule that says if you have log of a to the b, what's that equal to? B log a. So we could use that here to go to 2 log 1 over epsilon over log 1 over epsilon. And that's 2. Okay, so the definition of being two-dimensional means the number of balls that you need to cover that object scales inverse quadratically with the size of the balls. Okay, so the number of balls goes up quadratically as the size goes down. Here comes something slightly more interesting. The Cantor set. Middle third removed. Closely related to a homework problem on problem set 3. And I'm going to make a graphical table here. This is the iteration that we talked about before. And I'm going to make a table over here of as a function of the iteration number n, how many balls there are and what size they are, or how many chunks of the Cantor set there are. So in the first iteration, it has one piece, which is 1 long. In the second iteration, it has 2 pieces, each of which are 1/3 long. 3, 4, what's here?
1/9.
1/9. 4, 8, 1/27. What's the general pattern here? So n
2 to the n minus 1. 1 over n.
3 to the 1 minus n.
3 to the n, yeah.
Same thing, yeah. Okay, so that's the general pattern. So we can calculate the capacity dimension of this thing. I'm going to go, I don't have enough room here, so I'm going to flip a slide. So you got this, because this is homework stuff. Okay. If you want to be computer scientists, you can start this from 0 and make life a little bit nicer. Then it's just n over, then this is an n. Let me do this in different colors so you see what I'm doing. So if I call this 0, 1, 2, 3, then this would be n and this would be n. And if you like that better, that's fine. Okay. And these slides are all up on the web, or will be after class. So, capacity dimension of the middle third removed Cantor set. Now, here I talked about the iteration number n. How are the limit as n goes to infinity and the limit as epsilon goes to 0 related?
We can take 1 over epsilon.
So epsilon goes to 0 is the same as n goes to what?
Infinity 1 over.
Okay, right. N minus 1 goes to infinity, doesn't matter. Okay. Then we have the log of something over the log of something else. That's easy. What goes here?
1 over 3 to the... No.
This is?
Oh, the other one.
Okay, so it's 1 over 3. Wait a minute. Hang on a second. Let me make sure I get this right. So this is log of 2 to the n over log of 1 over 3 to the n. Or n minus 1, as you wish. Okay? Where'd that come from? Here is the number of balls to cover, and here is epsilon. So the definition is log of that middle column over log of 1 over that right column. And that's what's there. So that's equal to the same limit as n goes to infinity of log of 2 to the n minus 1 over log negative, right? No, 1 over 1 over. So I don't need a negative. Log of 3 to the n minus 1. Now we need the log of foo to the bar is bar log foo. We can use that twice. That will bring this down here and this down here. And the answer is, I'm not asking you to calculate that in your head. I'm asking you to cancel these. Log 2 over log 3, which is actually 0.63. Yes. Does that make sense? I'm just going to flip back a few slides for a second, and then I'll come back. Does that make sense given that picture? 0.63. It's between 0 and 1. That's good. Okay. For the Koch curve, it ends up being log of 4 over log of 3. I'm not going to derive that. That has to do with something that's this long becoming that long. So this is 3 long, and this is 4 times as long. So I should say the capacity dimension of the perimeter. is log of 4 over log of 3, so it's 1.26 or something like that. Again, I'm not going to do that. It has to do with the fact that at each step, each of those little chunks of edge that's 3 units long becomes 4 units long. And that's the iteration. Okay, so questions on these examples? John?
Is there any intuition to why it's 0.63 as opposed to something more attractive, like an even 2/3?
No, it's just because logs do that. Logs don't make nice results. But if you want to get if you want to pull an exponent out, a scaling exponent, a log is how you do it. So, yeah. So how would you do this for a middle something else, which is what's on your homework?
Change it through.
Would this change? No. Would this change? Would this change?
Yes.
Okay. So you can do this. I trust you. All right. So the summary of how to do fractal dimension. You cover the object, with balls of radius or diameter epsilon. So diameter or radius epsilon. Use that formula to take the limit. If the answer that you get is not an integer, then the thing that you were playing with is a fractal. It has fractal dimension. It has non-integer fractal dimension. That is the definition of a fractal. And again, the connection to chaos, why we do it in this course, is that many chaotic systems have various pieces of fractal stuff in their state space. So for example, you saw when you were doing problem set 1, something that looked kind of like this. Probably. Then, if you zoomed in on this, I don't know if you did or not, but you might have seen something like that. And then, if you zoomed in on this, you might have seen something like that. So this object that you created for the right R value, I don't know what R value would do this, something like 0.35 or 3.6, something like that. This is a fractal thing. You keep zooming in, and you'll see more structure. So the logistic map has fractal structure in its attractor. And also in its bifurcation diagram. And you saw that, I hope. So this is a self-similar object. Now I tried to draw something that wasn't exactly self-similar in the following sense. The zoom in, the yellow zoom in, you zoom in on something and you see 3 sets of dots. But then you zoom in on each of those sets of dots. Maybe you see 4 sets of dots. So it's not the case that it's 3 to 3 to 3 to 3. It might be 3 to 4 to 8 to 16. So it's not exactly self-similar, but it has features reminiscent of the whole. Okay, so again, one of the things about this course that makes it a challenge to teach and to take is that we have people from 7 or 8 different departments with lots of different backgrounds. So I try to offer some stuff for each of those sets of people, and so that means that there are going to be tangents that might either not be interesting to you as a member of one of those sets or might go over your head. And so don't worry if everything in this course doesn't connect. So for those of you who are mathematically more inclined, what do you think the measure of a Cantor set is? Lebesgue measure. In the limit of large iteration, they're all dots. So what's its measure? 0, in the sense that it can be covered by intervals whose total length is 0. Okay, so the measure of the thing how thick it is, how fat it is, how much space it occupies in the Lebesgue measure sense, which is the formal way to measure how thick something is 0. Okay? And then go back to this diagram in your heads. In the limit of large iteration, how many points does it have? First of all, infinite or finite? Infinite. But there are different kinds of infinities. There are countable infinities and there are uncountable infinities. Do you think this thing has countably or uncountably infinite number of points in it?
Countably. Uncountable.
I hear both voices. It's not obvious, but the way you think about whether something is countable is, you have some set and you want to know it's countable. You try to put it into one-to-one correspondence with the natural numbers, that is, positive integers. So you can show that a set is countable by associating each of its members with one of the integers, one of the positive integers. And if you can do that and there's none of either left over, then it's countably infinite. But this guy, the number of points doubles at every step. So it is actually uncountable. So it's an uncountably infinite set, which is part of what goes into the definition of fractal dimension and allows this thing to have dimension more than 0, is it has an uncountably infinite number of points. Again, it goes into those logs. Okay. If this kind of stuff is interesting to you, there's a couple of other fun examples in section 11.1 of Strogatz. Has some more examples like this. There are also, by the way, things called fat fractals. Fat fractals that have non-zero measure. I think York came up with that name too. He's good at naming stuff. So lots of esoteric kinds of creatures. Okay. I showed you a drawing, a sketch of fractal attractor structure in a map, the logistic diagram. Attractors in flows also have fractal structure in the following sense. If I take a Lorentz attractor and I slice it crosswise, what I'm going to see is where this attractor pierces this line is actually a Cantor set. Not a perfect middle nth removed Cantor set, but it's going to have a Cantor dust-like structure. So if you slice chaotic attractors crossways, you often, not always, often see Cantor set-like structure. And that's what I mean by fractal structure of attractors. There are other places where fractal stuff shows up in dynamical systems. Remember this picture that I drew of the attractor V living in the bottom of the basin of attraction W. So this is the basin. This is the attractor. This is the boundary of the basin of attraction. The metaphor that I used to talk about this picture was that V is the Atlantic Ocean, W is the terrain to the east of the Continental Divide, and this basin boundary is the Continental Divide. And the definition of attractors and basins is you start anywhere in the basin, you will eventually end up on the attractor in the limit of forward infinite time. And this is also the picture where we talked about dropping a whole bunch of points all the way through W. And by the way, W contains V. So this point here is both in W and in V. So we need to drop points everywhere in W. We let each of those points go forward in time separately, and that flock of points will end up collapsing down onto V together. Each of these points individually will do, something like this. But the whole crowd of them will spin and rotate and maybe just shrink down onto V. That's the definition of a basin and an attraction, basin of attraction and an attractor. Yes, sir?
What does this have to do with our notion of sensitivity to initial conditions? Because this seems like the opposite of insensitivity.
Yeah, so sensitive dependence on initial conditions, this is a good question, is something we talk about on an attractor. So it's semantics. So this point here and this point here will be they'll go different places, but sensitive dependence on initial conditions is a term that goes with the concept of being on a tractor and getting knocked sideways a little bit. It's just semantics. Okay? Now we talked about this before, but in continuous time systems, where you have to be able to draw this curve and be able to look at it at any time. That's what the definition of continuous time means, is time flows continuously along that curve. So we have to be able to look at it at any time. That implies, that's actually a sketch of a proof for why basins are connected. So if from each of these points, we have to be able to draw a continuous curve down to the basin, that's the definition of connectedness. So in a flow, the basin W has to be connected. In a map, that does not necessarily have to be the case, and I showed you a picture of a map whose basins of attraction are not connected. This is that Newton's method on x to the fourth minus 1 equals 0, and Newton's method wrapped around a nonlinear equation is a map that is designed to take a guess and improve that guess. So there's a iteration sequence under the operation of Newton's method such that the iterates of this map, the orbit of this map, the trajectory of this map converges to one of the roots of that equation. That is what Newton's method is designed to do. It doesn't really matter if you think of it that way, or if you think about it as a 2D map of the plane onto itself that takes points, maps them to the next point, and it has 4 attractors. One's here, one's here, one's here, and one's here. Those are 4 fixed point attractors of this map that is this thing wrapped in Newton. That's a map that takes xn and spits out xn plus 1. Okay? That map has 4 attractors, 4 fixed point attractors, and what this picture is a coloring of the basins of attraction of those 4 fixed points. All of the points that start out in red end up at the red fixed point, and so on and so forth. Now, we talked about this picture the other day, and everyone said it's very pretty in their heads, and they said, wow, it's complicated. One thing that's really interesting is this red chunk does not touch this red chunk. So the basins are disconnected and they're fractal. Okay, they're disconnected fractals. Also, the boundaries of those basins. If you tried to draw all the pixels that are at the edge of blue, you would get a structure that is fractal. Okay, so the basins of attraction and the boundaries of the basins of attraction in this map are fractals. Okay, and this is exactly the question that was brought up before. Fractal basin boundaries can occupy a tremendous amount of the space. And when you're near a fractal basin boundary, the future time evolution of that initial condition could depend a lot on small changes. Right? Makes sense? So if you're right here, then if you move a little bit one way or the other, you could go, that guess could converge to any of the 4 roots. So the fractal basin boundaries can occupy lots of space, and that can cause the trajectory to be very sensitive to the initial condition. But semantics-wise, that is not the same thing as sensitive dependence on initial condition, because this is defined on a chaotic attractor. And someone anticipated this, rightly so. Sensitive dependence on initial conditions is you're on a chaotic attractor, you're running around a chaotic attractor, and something bumps you sideways a little bit. That's what we are thinking about when we use this term. What's going on here is that the raindrop is near the continental divide, And the wind, if it blows it a little bit, might blow it across the continental divide, which would cause it to roll to the Pacific and not the Atlantic. That is hugely sensitive, but is not what's called sensitive dependence on initial conditions. Again, just semantics. Okay, so don't get those confused. I realize that they're both pretty sensitive, and they're both sensitive to initial conditions. By the way, also, initial conditions, not parameters. Okay, so sensitive dependence on initial conditions means state, not parameters. You don't think of, and again, this is just semantics and definitions, but it's important to get the language down. Okay, I seem to have scribbled on this already, my apologies. Fractal basins and fractal basin boundaries and all that kind of stuff does not just occur in mathematical examples like this, it also occurs in physical examples like this one. What this is a physical pendulum made out of some iron or something like that. And we're looking down at it from the top. The pendulum is suspended from a point above the sheet right here. And there are 3 magnets embedded in the sheet. And so if the pendulum, if you could just look at me for a second, the pendulum's swinging, and there's 3 magnets here. And the pendulum gets attracted to each of them. If you start the pendulum over one magnet, it'll stick there. If you start over this one, it'll stick there. And so what's on that picture is, again, color-coded. There are 3 fixed points. Each one is color-coded, and if you start anywhere in the red, that is, if you start the pendulum in any of the red points, it'll eventually get stuck to the red magnet, and so on and so forth. So fractal basin boundaries and fractal basins occur in physical things too. But there's something wrong with this picture. There's something that should be upsetting about this picture. This is a flow. Basins and flow have to be connected. And those basins sure don't look connected. So what I've actually showed you here is not a state space portrait. What I've actually showed you is what's called a Poincaré section. So Poincaré section, should be accent aigu there, is essentially slicing. Okay, so imagine if you have some limit cycle like that, and you take just a knife, a cake cutter, and you slice it. What are you going to see? So the purple thing's living in 3D, and I take a plane of section, a 2-dimensional plane of section, and I use that to slice the Poincaré section. Sorry, slice the periodic orbit. What am I going to see? You've all read Flatland, right? Okay, I'm in Flatland. What am I going to see? What piece of that purple thing am I going to see? Just a dot, right? Okay, so a Poincaré section is a way of reducing information. It's a way of reducing information. Essentially, it's a codimension 1, so it takes a slice, it takes a dimension n thing, it brings it down to a slower dimension. That's what's going on here, is this picture is actually a Poincaré section of this flow. So this is really a Poincaré section of a flow, of a physical flow, that someone constructed by doing something like this. And when you do something like that, it's just like flashing a strobe light at the trajectory. So it's just like flashing a strobe light at the trajectory. There's a flow, and if you sample it at discrete times, you've basically taken continuous time and you've made it discrete, and so that makes it kosher that this thing is disconnected. So it's okay that this is disconnected because this operation was used to construct it, and that operation essentially discretizes time and turns a flow into a map. Okay? So bifurcations, which we've talked about, somebody turns some sort of knob and the attractor changes. Somebody turns that knob, the attractor changes, the basin can also change. So basins and their boundaries can be affected by attractors. So bifurcations don't just affect the attractor geometry. So bifurcations affect the geometry of attractors, their basins, and their boundaries, those boundaries of those basins. Okay. And often, not always, fractal basin boundaries are left in the state space of a dynamical system because they're the ghosts of dead chaotic attractors. So there's some chaotic attractor, and then somebody turns a knob, and that attractor undergoes a bifurcation which makes it unstable, but it still leaves its signature in the dynamics even though it's unstable, much like these veils in the logistic map. Again, I mentioned this before. If you take this guy and you trace it back, it ends up kind of connecting to this. So this is a periodic orbit. This is an unstable periodic orbit. And you can see kind of from the connectedness structure of the bifurcation diagram that it sure looks suspiciously like the unstable periodic orbits kind of are left over after, or they follow from the periodic orbits. And I can make that a lot more precise later on. There's a whole series of papers by Svetanovich about this. But just for now, unstable periodic orbits don't go away. They just lose, or sorry, the other way around. Periodic orbits don't necessarily vanish. They just lose their stability, and they turn into unstable periodic orbits. And this plot shows that, and we'll get back to some more of that. In the same way, fractal basin boundaries are often the ghosts of dead chaotic attractors. So someplace in some previous incarnation with some previous parameter value, this system had a chaotic attractor lying around on the diagonal. And then some parameter changed, and that chaotic attractor died, rather, it just lost its stability. It's leaving its tracks in the dynamics still because it's a chaotic a fractal basin boundary. Again, this can be how they arise. And just to revisit a little bit about dimensions, fractal basin boundaries can arise in 2D maps or bigger, or 3D maps, 3D flows are bigger. So there's some restrictions on dimension there. Capacity dimension is just one kind of dimension. There are 20 or 30, 40 different kinds of dimension. We'll talk about 3 or 4. Capacity dimension, if you recall, is the one where you're covering the object with balls of radius epsilon, changing the size of the balls, repeating the covering, and looking at the pattern with which the number of balls you need scales with the inverse of the size of the balls. Another member of the family is called similarity dimension. I'll probably just finish up with this. It only works with fractals that are exactly self-similar. So it only works for exactly self-similar fractals. And here's how it works. It's based on exactly how many shrunken copies of itself an object contains. So if you have an object that looks like this, and then the iteration sequence looks like this, and so on and so forth. The idea? So the iteration, at each iteration, you take something that's half the size and you make 4 copies. So the iteration here is, at each iteration, you make 4 copies of yourself, and each one is 1/2 the size. Okay, so you have the iteration is halve your size and make 4 copies of yourself, and so on and so forth. Then the similarity dimension is defined as any kind of log you want of m over any kind of log you want over r. What's missing here that was in the capacity dimension? A limit. Why don't we need a limit here?
Doesn't depend. It's self-similar.
Right? At every iteration, at every time click, the change is the same. So there's no limit. And that's because, I shouldn't use that. I should use this because of that. Okay? So the ratio captures the dimensionality here. What about this example here? Say I have this object. What's the similarity dimension here? What's M? And R is 3, so it would be, is it different? So here, this would be log of 4 over log of 2, which is log of 2 squared over 2. And this is log of 3 squared over 3. So the same. Okay. All right, so we will pick this up next time. And what we'll start with is how to calculate this from data.